1987 E3, and unfortunately the page break separated the diagram from the problem. So in the diagram we have a 20 volt battery in series with a 10 ohm resistor, and then a junction so that we have a 90 ohm resistor and a 0.5 Henry inductor, and then a switch down there. So when we close the switch, the inductor will not have had any current in it, so all of the current will go through the 90 ohm resistor. After a very long time, the current in the inductor will have built up, and all of the current will go through the inductor, and none will go through the resistor. Meanwhile, however much current there is going to be going through the 10 ohm resistor here because that's in series with the battery. So let's take a look at what they want us to find here. For the instant immediately after the switch is closed. Okay, so immediately after the switch is closed for parts A and B, that guy basically doesn't exist, and our circuit is just battery, 10 ohm, 90 ohm, and then the switch. So for part A, the potential difference across the 90 ohm resistor. So again, just the instant after the switch is closed, at t equal to 0, I of the inductor is equal to 0. And what we have is our total is going to be 10 plus 90 equals 100 ohms. And using the Kirchhoff loop rule, we will have voltage of the battery minus voltage of the 10 minus voltage of the 90 equals 0. And then we will have voltage of the battery minus IR minus I of the other R. Now, because these two guys are in series, those two I's are the same. So we will have 20 volts there, I, 100 ohms here, and we're going to have a current of 0.2 amps. That doesn't answer the question for part A. What it does is set us up so that we can go back to here and find the voltage across the 90 using Ohm's law, 0.2 times 90 ohms, and that gets us 18 volts. That's an 8. 18 volts. All right, for part B, the rate of change of current in the inductor. Now, they asked us for the voltage of the 90 ohm because the voltage of the 90 ohm is going to be the same as the voltage of the inductor. So for part B, because those guys are in parallel, things in parallel have same voltage. So voltage, why is that a B? That doesn't make any sense. So voltage of the 90 equals voltage of the inductor. So this will be 18 volts equals L di dt, which is what they want us to find. They say the rate of change of current in the inductor. Remember, rate of change means derivative. And the voltage of the inductor is L di dt, and they told us what L was. That was 0.5. So di dt is going to be 36 amps per second. That's how quickly the current is building up in the inductor. Now I'm going to have to pause for a second to clear out the entire right side here so that I have the space for the rest of the problem. All right, for parts C and D, they say, okay, we've had the switch closed for a long time. Now what's going on? Now, when the switch has been closed for a long time, the inductor acts like a battery, a wire, a perfect wire, and the resistor over here essentially is cut out of the circuit. We've switched which one of these branches all of the current is going in. So how much current is in the inductor now? Well, our Kirchhoff loop rule for this long time later is going to have our battery and the 10 ohm resistor and the inductor and not the 90 ohm resistor. Now, after the current has built up in the inductor, that means it doesn't have any voltage across it. There's going to be no voltage across a perfect inductor. So the current in the inductor is going to be whatever the current is in this 10 ohm resistor. So we're going to have 20 volts minus the current times 10 ohms is 0. So the current is going to be 2 amps. Whatever the current is in the 10 ohm resistor is going to be the current in the inductor because they are now perfectly in series. Part D. The energy stored in the inductor. All right, the energy stored in the inductor, so UL, is a lot like kinetic energy. L is like mass and current is like velocity. So 1/2 Li squared. So 1/2 of 0.5 of 2 squared, which gets us to be 1 joule. Now in 1987, this is a little bit harder problem than it is now because in 1987, I don't think they were giving equation sheets. So you actually had to have this memorized. You have an equation sheet. You won't have to have that memorized if they even put an inductor on your test. My guess, it's going to be something with a capacitor, is my guess. Later at time t0. Okay, now we're going to reopen the switch. And if you notice, when we reopen the switch, what we've done is we have eliminated the 10 ohm resistor and the battery. And now the current is just the 90 ohm and the inductor. And whatever the current was in the inductor the instant before we open the switch, that's going to be the current now, and now it's going to get forced through the 90 ohm resistor. So for the instant immediately after the switch is opened, what's the potential difference across the resistor? Well, the current in the inductor is still going to be 2 amps. And now that current is going to be the current in the 90 ohm resistor. It's also 2 amps. Once you know a current in a resistor, now you know the voltage across the resistor. Wait a second, where'd that 18 come from? That's 90. So that'll be 180 volts. That's where that 18 come from. The answer is 180. All right. Now that's just for that instant because remember, voltage of the inductor is going to be L di dt. In order to have a voltage across an inductor, you have to have current changing in the inductor. Opening the switch forces there to be a voltage across the inductor because now we have a voltage across the resistor, and these two voltages have to be equal by, again, up here, Kirchhoff's loop rule. So we subtract these two guys, we need to get 0 because they're the only two guys in the circuit right now. So the voltage across the inductor is going to be 180, and then this is 0.5, and that instant after the switch is opened, we're going to have a change in current in the inductor of 360 amps per second. So that current is going to be dying out really, really fast. They didn't ask us about the current, they asked us about the potential difference, but they're going to follow the similar curve. It's going to be an exponential decay. So in the axis below, sketch the potential difference for that. So it's going to start out at 180 volts, and then it's going to die out with an exponential decay.